Greetings of the day. I welcome you to lecture number 34 of Power Quality Problems and Solutions. In today's lecture, I am going to discuss with you the Dvr compensation implementation. I mean, how can we implement practically the voltage compensation done by the Dvr. I will write here Dvr compensation implementation. Dvr compensation implementation. First of all, we will take implementation of single phase DVR, and we will later on extend the same to three phase DVR. Implementation of DVR for single phase system. So we have to basically do the series compensation, or we have to do the voltage compensation. Let us first of all consider a single phase system. So in a single phase system, we assume first of all that full system information is available. And for implementation of single phase DVR, following steps will be followed by us. But before I go to that, let me discuss with you the phasor diagram, generalized phasor diagram, which we have already discussed in the previous class. This is our load voltage phasor, and this should be equal to source voltage phasor. That is the one of the objectives. I mean, even if there are voltage sags, voltage swells, or voltage drop across the feeder, that should be taken care of by DVR. DVR should inject the voltage VF, and that injected voltage should take care of voltage drops or voltage changes, and it should try to make load voltage always equal to source voltage. So this is the trajectory of your load voltage, and it should be equal to source voltage. It's a circular trajectory, as you know. So I will write here trajectory of load voltage or source voltage. Okay, so this is one possibility if feeder resistance is neglected. I mean, if this is the load current or system current I at a phase angle of phi L, so this will be source voltage here, Vs. Let us assume the system has some resistance, feeder resistance is there, and feeder resistance voltage drop is in phase with the current. And suppose this is feeder resistance voltage drop. This is I into Rs. Rs is the feeder resistance, series resistance of the feeder. Then this is the locus. I will write here, this is the locus of Vf minus Ji xs. Because if you remember, we have already derived one equation in previous class, and that that equation was Vs is equal to, that is source voltage is equal to load voltage plus a resistive voltage drop minus DVR injected voltage or compensation voltage minus Ji into xs. We know that resistive voltage drop and this reactive voltage drop causes load voltage to be less than source voltage. From this, if you write load voltage will be source voltage minus resistive voltage drop plus Vf minus Ji into xs. I mean, this resistive voltage drop and reactive voltage drop cause load voltage to be less than source voltage. What does your DVR do? It injects a compensation voltage Vf, or you call it filter voltage, so that this Vf minus Ji xs, it compensates for both resistive voltage drop as well as reactive voltage drop, and the sum of these two phasors, that's IRS plus Vf minus Ji xs, is equal to 0. giving load voltage equal to source voltage. So therefore the locus of this Vf minus Ji axis, okay, this is the locus of Vf minus Ji axis, and you can see it intersects this trajectory of Vs at 2 points. This is point A and this is point B. So therefore this becomes your source voltage, or this is another solution, this becomes your source voltage. So therefore you can see your load voltage is exactly equal to source voltage. So what does, if you take this as solution, because here the injected voltage is less, so you can see this is the locus of Vf minus Ji axis. What it does, it compensates for resistive voltage drop and reactive voltage drop, and it brings the vector back in such a way that load voltage becomes equal to source voltage. Okay, and now you can see from this phasor diagram that this injected voltage, if you consider this injected voltage Vf, this injected voltage is at 90 degrees with the current. See, this is the current, load current, which is same as the current flowing through the Dvr transformer. And then this is your injected voltage Dvr, injected voltage Vf, because you can see this Vf is at 90 degrees to this. So therefore, what is Dvr power? Dvr power is voltage, compensation voltage into current. And since voltage and current are at 90 degrees, it means Dvr is injecting only reactive power, QF. It is not injecting any active power. So therefore, Dvr does not need any, energy source at its DC bus. A simple DC bus capacitor, which acts as an energy storage device, can be used at the DC bus of the Dvr. And therefore, the Dvr injected voltage should be in quadrature with the current. That means when you calculate the angle, phase angle of Dvr injected voltage or compensation voltage, this angle should be 90 degrees with respect to the current. Okay, so that Dvr injects only reactive power to make load voltage equal to source voltage. That means to make the voltage compensation, to do the voltage compensation or series compensation. So with this as the background knowledge, following are the steps for Dvr implementation. The idea is to calculate this Vf star, that is Dvr injected voltage we want to calculate, reference voltage. And we know that Vf star in one of the previous classes, it is given by this equation, Vf minus 2 into 1 plus A2 into A1 plus B1 B2 into Vf plus 1 plus A2 whole square plus B2 square minus 1 equal to 0. If you know A1, if you know A2, if you know B1, if you know B2, you can find this is Vf square here. You can find this Dvr injected voltage. And from here, Dvr injected voltage will have two values, which will give two solutions, A and B. For smaller rating of Dvr, we will take lower value of Vf, and that will be our Vf star. That is a reference filter voltage or reference compensator voltage. And then Dvr should inject that voltage. I mean, when you implement the Dvr, Dvr should act as a voltage source, and it should inject a voltage Vf, which is very nearly equal to this reference injected voltage, which you get from this equation. It should be very nearly equal to Vf star. And to synthesize this voltage source, in which the injected voltage follows very closely the reference voltage, reference injected voltage or reference compensation voltage, this voltage source can be synthesized by a voltage source inverter, which we call as dynamic voltage restorer, DVR. So therefore various steps, so therefore you need the information about A1, A2, B1 and B2. And from previous class, you know that when you find the DVR injected voltage, it's at an angle of say Vf, and it is equal to Vf into A2 plus JB2. If you know the angle of DVR, so that will have a real part and reactive part. So from that angle information, phase angle information of DVR, you will be able to find A2 and B2. Okay, A2 as well as B2. A1 and B1, where from you will get A1 and B1. you will be able to find A1 or A1 B1 or A2 B2. Let me verify it again. I think you will be able to find A1 B1. Yeah, it is A1 B1 here, not A2 B2. So you will be able to find A1 and B1. And what is A2 B2? That is equal to I into RS plus J XS. That is equal to A2 plus J B2. If you know the load current, you know feeder impedance, that is feeder resistance and feeder reactance. Substitute here, you will get some value, say current at some value angle, say at some angle theta. That theta will have a real part and reactive part. That will give you A2 and B2. Then you will substitute this A1, B1, A2, B2 information in the equation, quadratic equation, from where you will get VF star. And then you will implement that VF star. You will synthesize this voltage using a voltage source inverter, which acts as a DVR. So what are the steps for implementation of DVR for single phase system voltage compensation? Following are the steps. Number one, what is the first step? Define a reference quantity. Let us define a reference quantity such as we can define load voltage or we can define terminal voltage. Terminal voltage. So we call that VT ref. Okay. All other quantities will be synchronized to it. All other quantities that we will calculate are synchronized to this reference voltage VT ref. Okay, this is the first step. The second step is you have to calculate the angle of this compensator voltage, compensation voltage. इसका angle पता होना चाहिए, which is equal to VF A1 plus JB1, जहाँ से आपको A1 और B1 मिले. I told you that in order to ensure that when DVR does the series voltage compensation, it injects only the reactive power. That means if this is current, the injected voltage VF should be at 90 degrees with respect to this current. Right? Taking the terminal voltage VT ref as a reference, what you do, you find the phase angle of the current with respect to this terminal voltage. Okay? And then the phase angle of the compensation voltage will be phase angle of current plus 90 degrees. Why plus 90 degrees? Because this compensation voltage should be at 90 degrees to the DVR current, to the current. So that DVR injects only the reactive power, not active power. Okay? So therefore, second step is that find the phase angle of DVR voltage from fundamental component of line current. उसका मतलब हुआ, that is extract, if your load current is if your load is non-linear and load current is having harmonics also, what you have to do? You have to extract the fundamental component of load current. Extract the fundamental component of load current. Load current. अगर load linear है, then you don't need to extract the fundamental current, because in that case load current is itself a fundamental component only. It does not have any harmonics. But if load is non-linear, then in addition to fundamental component, your load current will have harmonics also. So from that distorted current, you have to extract the fundamental component of load current I1 using Fourier transform. So you can use Fourier transform, and using Fourier transform, you can find the fundamental component of load current from the distorted current. Once you know the fundamental component of load current, you will have its angle also. So therefore, what will be the angle of compensation voltage? Its angle will be the angle of fundamental component of current plus 90 degrees. You shift this, whatever angle is when you extract the fundamental component of load current. it will give you information about the phase angle of the current with respect to this reference, that is terminal voltage. You shift that phase angle of current by 90 degrees in order to ensure that the DVR injects a voltage which is at 90 degrees to the current. Okay, and so that DVR injects only the reactive power for voltage compensation, no active power is required. Okay, so therefore the angle of DVR voltage is found like this. From this you find the angle of, when you extract the fundamental component of load current using Fourier transform, it will give you information about the phase angle of fundamental component of load component of load current with respect to this terminal voltage, which is reference, with respect to reference. So shift that phase angle of current by 90 degrees. I have shown you in previous class how to do it with the help of numerical problem. We have done this in one of the previous classes, in fact previous class itself. So shift this phase angle of current by 90 degrees. So that will give you VF A1 plus J B1. Once you know the phase angle of the compensation voltage, it will have real part and it will have reactive part. So you will come to know what is A1, you will come to know what is B1. Okay, so this is step number 2. What is the step number 3? Step number 3 is, in step number 3 you have to find A2, B2. So from the information of feeder impedance, get A2 and B2 as, because the current multiplied by feeder impedance, that's RS plus JXS, we already know it is equal to A2 plus JB2. You know what is the load current, because you know load kitne kVA ka hai ya kitne MVA ka hai, so you can very easily find load current. Multiply that by the feeder impedance, feeder resistance plus reactance. So I into RS plus JXS, that will give you A2 plus JB2. यहाँ से आपको A2 का पता चलेगा and you will come to know about B2. So once you have all the information, you know what is A1, what is B1, what is A2, what is B2. So the last step is, so step number 4 is find VF star, that is reference compensation voltage, from which equation? From this equation. From this equation, that is VF star square minus 2 into 1 plus A2 into A1 plus B1 into B2 into VF star plus 1 plus A2 whole square plus B2 square minus 1 equal to 0. This is the quadratic equation for the Dvr compensation voltage, which we have developed in previous class, in the last class. So from this quadratic equation, you were not knowing the values of these A1, A2, B1, B2. From last 3 steps, you come to know what is A1, what is A2, what is B1, what is B2. Substitute in this equation. This will give you a reference value of compensation voltage, VF star. Once you know what is the reference value of compensation voltage, that means you know what type of voltage has to be injected in series with the load bus for voltage compensation or for series compensation. Now, how to synthesize this? Because this is the mathematical from mathematical calculation, you will come to know, what will be VF star? VF star will be root 2 into VF star sine of omega t plus angle of VF star. Okay. So you can find instantaneous value of this injected voltage, compensation voltage. That is, यहाँ से आपको RMS value मिलेगा from this equation. Multiply that by root 2. So that is root 2 into VF star sine of omega t plus VF. So that is equal to VF star is equal to root 2 VF star sine of omega t plus, what is the angle? Angle is phase angle of current plus 90 degrees, जो आपने already निकाला हुआ है previously. So substitute in this, you will get the nature of compensation voltage. Now the question is how to inject this. So therefore you have to synthesize a voltage source like this, which will inject Vf star, which is given by this equation. And how did we get this Vf star? From these 4 steps. Now how to synthesize this Vf star, this voltage source? That is in step number 5. Synthesize Vf star using a voltage source inverter, which is called DVR, dynamic voltage restorer. So you will have a dynamic voltage restorer, which is basically a voltage source inverter, which has DC input and AC output, and do the switching of the switches of this voltage source inverter should be done. The switching should be done in a particular fashion. How control pulses are generated? We generate the control pulses from a control algorithm when you implement a control algorithm. And from that control algorithm, basically you find Vf star. And then you have to make Vf nearly follow the Vf star, so that the DVR or this voltage source inverter produces a voltage at its output and injects that voltage in series with the load bus. And that injected voltage should be very nearly equal to this reference injection voltage or reference compensation voltage. So that can be done by proper or particular or switching of the switches of the voltage source inverter. When voltage source inverter switches are switched in a particular fashion, how do we do that? How do we generate the control pulses? I will come to that in a minute's time. So the switching of the IGBTs or switches of voltage source inverter will synthesize this voltage source, and it will generate at its output a voltage Vf, which is very nearly equal to Vf star, and it will inject that voltage in series with the load bus, and it will do the load compensation. Okay, so this is for single phase system. The same can be done for a 3-phase system. Now 3-phase, so before we go for 3-phase system, let me tell you that when you find this Vf, for example, Vf square star minus 2 into 1 plus A2 into A1 plus B1 into B2 into Vf star. This is capital Vf, not small vf, Vf star, plus 1 plus A2 whole square plus B2 square minus 1 equal to 0. When you implement, when you find Vf star from here, from this quadratic equation, the reference filter voltage, you need all the information of the system. You need full information of the system. You need the information about what is the feeder resistance, what is the feeder reactance. Because you know I into Rs plus Jxs is equal to A2 plus JB2. You can find A2 plus JB2 only when you have the information about what is the load current and what is the feeder resistance and reactance. If you don't have the knowledge of feeder impedance, you cannot find A2 plus JB2 and you cannot substitute that here. So this type of method in which you need full information of the system, this is called type 1 control. This is type 1 control. And it is a bit complex in the sense that sometimes you may not have, for example, you go to the field as an engineer and you want to implement this voltage compensation through DVR. So when you have to implement the DVR, you have to synthesize a voltage, injection voltage using a voltage source inverter, a DVR. You have to design that DVR. You have to design its control algorithm so that it injects the voltage Vf, which is very nearly equal to the reference voltage. In order to find the reference voltage mathematically, you need the information of feeder impedance. It is possible that you may not be given the info, or you may not have the information about the feeder resistance or feeder impedance. Then there will be problem. That type 1 control will be difficult to implement because you may not have information about feeder impedance. So to make the things very easy, we go for another type of control, which is called type 2 control. What in type 2 control, we write the terminal voltage. For example, you already know terminal voltage is equal to load voltage minus DVR injected voltage. Okay, and your load voltage is at an angle of 0 degree because you take load voltage, for example, as a reference, minus Vf is Vf A1 plus J B1. Okay, now your terminal voltage, for example, Vt, is at an angle of delta. because this terminal voltage also has its own phase angle. Let us call that phase angle as delta. That is equal to VL at an angle of 0 degree. VL at an angle of 0 degree means VL itself, minus A into A1 into VF minus J B1 into VF. Okay. Now what is this? This is VT. What does angle alpha means? It means cos. What does angle delta mean? It means cos delta plus J sine delta is equal to, let me take real parts here, VL minus A1 VF minus reactive part is this minus JB1 into VF. Let us square the real and imaginary reactive terms, real and imaginary terms. We square them separately. So this will be VT square into square of real term here is cos square delta plus square of imaginary term is sine square delta is equal to square of this real term. So VL minus A1 VF whole square plus square of imaginary term, that is V1 VF whole square. What is cos square delta plus sine square delta? That is 1. So therefore we will write VT square is equal to, this is A minus B whole square, that is A square plus B square. B square is A1 VF whole square minus 2AB 2 VL A1 VF plus this is B1 VF whole square, or this is VT square is equal to VL square plus this is here A1 square VF square. I will take this also here. This is plus B1 square VF square minus 2A1 VL VF. Okay. So further simplification will give me, it will give me this equation. That is, I have here VF square. If I take VF square common from these terms, I will get A1 square plus B1 square. So it is A1 square plus B1 square. Then I have this term minus 2A1 VL VF. Okay. Then we have plus VL square, and we will shift this to other side. So this will be minus VT square equal to 0. And by the way, what is A1 square plus B1 square? We have seen in the previous class also it is equal to 1. So therefore we will get VF, let us call this star square, reference voltage. A square plus A1 square plus B1 square is 1 minus 2A1 VL into VF star plus VL square minus VT square is equal to 0. This is the equation, and from here you can find the reference compensation voltage. It's a quadratic equation, so it will give the two values of VF star. Take the lower value. So here you need the only one information. You need the information about A1 only. In the previous equation, you needed the information of A1, A2, B1 and B2. Okay, A1 and B1 you get from phase angle of this VF, phase angle of VF, that is equal to A1 plus JB1, and it is very easy to find. If you know the phase angle of current, you extract the fundamental component of current using Fourier transform, find its phase angle, and then phase angle of VF will be phase angle of current plus 90 degrees, and that is equal to A1 plus JB1. So you can find A1 and B1, it is easy. But how do you find A2 and B2? A2 and B2 in previous equation you had to find from this equation. I into Rs plus Jxs is A2 plus JB2. For that you needed to have the knowledge of feeder impedance. So if you don't know feeder resistance, you don't know feeder reactance, that's you don't have any information about feeder impedance, then you could not find A2 and B2, and you don't require A2 and B2 in this equation. In this equation, you need the knowledge about A1. A1 is very easily found from phase angle of this compensation voltage. Load voltage you already know. Put a voltage sensor across the load, that will give you load voltage. And VT is the terminal voltage, which you have taken as reference, that's all. So you need limited information in this type of control. You need the information about A1 only. The A1 can be very easily found from the phase angle of compensation voltage, and you need the information about terminal voltage and load voltage, which you can find very easily with the help of voltage sensors. You don't need any knowledge or any information about feeder impedance. So this equation makes computation of compensation voltage, reference compensation voltage, very easy. And this type of control is called type 2 control. Let us call this equation as equation B, and previous equation we call as equation A. This is equation A and this is equation B. You can find VF star from both equations, from this equation as well as from this equation. But in equation A, you need the information about feeder impedance. In this equation, you don't need any information about feeder impedance. So this is a better solution. So this is called type A control, this is type 1 control, and this is called type 2 control. Now let us see how we can implement the DVR compensation in three-phase systems. We'll take two different cases. I will not discuss three-phase systems. DVR voltage compensation or series compensation in three-phase systems. I will take two cases. Case A is three-phase unbalanced system but sinusoidal. Three-phase unbalanced sinusoidal system. I mean, load is linear, that's why it is sinusoidal system. Load is not non-linear, and voltage itself is also sinusoidal. So it's a three-phase system which is the three voltages or three source voltages are sinusoidal, but unbalanced voltages are there. So you have to use DVR here for compensation. Now the job of DVR is to balance these voltages and regulate these voltages, make these voltages equal to source voltage. So voltage compensation has to be done. What are the steps? What is the step 1? Step 1 as usual is take reference value, take VT, that's terminal voltage, that is VTA, VTB and VTC, because it is a three-phase system, as reference voltages. Okay, that is step 1. Step 2 is extract positive sequence fundamental components of load currents, that is IA1 plus, okay, IA plus, fundamental I should not write because the system is not having harmonics, so it is extract positive sequence components of load currents IA plus, IB plus, IC plus using Fourier transform. Okay, you have a Fourier transform algorithm. In your control algorithm, implement that Fourier transform. You will have three current sensors which will sense the three load currents. What are the three load currents? Say IA, IB, IC. Now these are unbalanced currents. Then using Fourier transform algorithm, what that algorithm will do, from these three unbalanced currents, it will extract the positive sequence components of currents. Because positive sequence components of currents represent a balanced set of three-phase currents. So it will extract IA plus, IB plus and IC plus, this Fourier transform. So therefore, once you know IA plus, IB plus, IC plus, you know about their angles also. You know angle of IA plus, because it will give you information about phase angles of currents also. IA plus, IB plus angle and angle of phase angle of IC plus. Once you have the information about phase angles of the three line currents or three phase currents, in step 3, you have to find phase angles of reference compensation voltages or injected DVR injection voltages. Okay, so that आपके पास 3 इंजेक्शन वोल्टेजेस है. VFA, इसका एंगल आप फाइंड कर लीजिए. What is that angle equal to? That is phase angle of positive sequence component of current, जो आपको यहाँ से मिल गया, plus shifted by 90 degrees. In order to ensure that your DVR does the series voltage compensation by injecting only reactive power, the injection voltages, reference injection voltages should be shifted by 90 degrees so that these reference voltages are at 90 degrees or in quadrature with the currents. Okay. Similarly, phase angle of VFB should be equal to IB plus, that is phase angle of positive sequence component of line current IB plus shifted by 90 degrees. You have to do it mathematically in the control algorithm itself. So in the control algorithm, you will find phase angle of Dvr compensation voltage or injection voltage, that is phase angle VFC. You have the information of positive sequence component of line current IC, add 90 degrees to it, so that will mathematically give you the phase angle of VFC. Okay. Once you have done this, you have now two equations, equation A or equation B. So in step number 4, that is step 4, find reference compensation or reference injection voltages VFA star, VFB star, VFC star using equation A. अगर आप for type 1 control, if you want type 1 control, I mean अगर आपके पास feeder की information है, feeder impedance information, then you can use equation A, because in that equation you need the information about the feeder resistance and reactance. So you can use type 1 control or using equation B, जो अभी थोड़ी देर पहले हमने लिखी थी, for type 2 control. If you don't have the information about feeder impedance, you don't know what is feeder resistance, how much is feeder reactance, use equation B for type 2 control. Okay, तो आपके पास अब 3 equations आएंगी आपके पास. I mean, you can go for type 1 control or type 2 control, whichever control you use. You can find RMS values of reference compensation voltages VFA star, VFB star and VFC star, right? So therefore, what will be instantaneous value of VFA star? That will be root 2 into RMS value of VFA star sine of omega t plus phase angle of VFA. Okay, phase angle of VFA आपने step 3 में निकाला, you know, current का IA plus का phase angle, positive sequence component of phase A current का phase angle आपको पता था, you shifted that by 90 degrees and that will be angle of VFA. वो यहाँ substitute कर लीजिए. It will not be root 2 VFA sin omega t, it will be root 2 VFA sin of omega t plus this. Okay, similarly VFB star will be equal to root 2 VFB star, जो कैपिटल VFB स्टार है, RMS वैल्यू जो आपने यहाँ से निकाला स्टेप 4 से, साइन ऑफ ओमेगा टी माइनस 120 डिग्रीज प्लस फेज एंगल ऑफ VFB एंड VFC स्टार इज इक्वल टू रूट 2 VFC स्टार साइन ऑफ ओमेगा टी प्लस 120 डिग्रीज प्लस फेज एंगल VFC. ओके, तो ये आपकी 3 रेफरेंस वोल्टेजेस बन गई. Now how to synthesize these reference voltages using voltage source inverter or using DVR, I will come to that. So this was for 3-phase unbalanced sinusoidal system. Let us assume now that our system is unbalanced as well as non-sinusoidal. Now how can we implement DVR in that case? DVR compensation voltage कैसे हम implement करें? Let us see. That is case P. 3-phase unbalanced non-sinusoidal system. Non-sinusoidal system. Now our system is unbalanced as well as non-sinusoidal. So therefore आपके DVR का काम क्या है? DVR has 3 objectives. Number 1, voltage regulation. It has to make load voltage equal to source voltage. Number 2, voltage balancing. 3 source voltages are unbalanced, but it has to balance them so that load के across balanced voltages मिले. And number 3, harmonic compensation. Harmonic compensation, because you can see your system is non-sinusoidal, So the three voltages are rich in harmonics. It has to cancel those harmonics so that जो critical load है, voltage sensitive load है, उसके across जो voltage मिले, that is harmonic free. So therefore, if this is your critical load, I will write here critical load or voltage sensitive load. It will get purely sinusoidal voltage because harmonic compensation will be done by DVR. It will get three-phase balanced voltages because voltage balancing will also be done by the DVR, and it will get regulated voltage, constant voltage, even if source voltage में dips आ जाते हैं, sags, swells या voltage feeder में drop होती है, but it will make load voltage constant and equal to source voltage. So these three functions will have to be done by your DVR. Let us see how DVR does that. So here the terminal voltages VTA, VTB and VTC are resolved into their fundamental positive sequence voltages and rest part. I mean आपकी terminal voltage VTA हम reference मानते हैं, हमने पिछले केस में भी reference माना, single phase केस में भी इसको reference माना. Now in this case the difference being this terminal voltage is unbalanced as well as it has harmonics also. So therefore what you will do, आप इसका fundamental component extract करोगे. You will sense the three terminal voltages with three phase terminal voltages with the help of voltage sensors and use Fourier transform. With the help of Fourier transform you will find their fundamental component and positive sequence component VTA1 plus. और जो बाकी बचता है, that is VT, this is VTA1 plus VTA rest. Rest means when you extract the positive sequence fundamental component, what is left? Negative sequence component and harmonics. So positive sequence component you have extracted using Fourier transform and fundamental component. What is this VTA rest comprising of? It will comprise of negative sequence component and maybe zero sequence component, which gives rise to unbalance, and it will also comprise of harmonics. Similarly, VTB आप mathematically अपने control algorithm में उसमें से VTB1 extract करेंगे and it will be plus VTB rest, and VTC will be equal to VTC1 plus VTC rest. तो ये आपके पास तीन टर्मिनल वोल्टेजेस आ गई. उसके बाद सेम स्टेप्स यू हैव टू फॉलो. स्टेप वन, दिस इज ऑफ कोर्स योर स्टेप वन. दिस इज स्टेप वन. स्टेप वन में आपने ये you have resolved your terminal voltages into positive sequence fundamental components and rest. What is step 2? In step 2 you have to extract fundamental components of load currents, that is a plus positive sequence component and fundamental IB1 plus and IC1 plus using Fourier transform. Once you have done, आपको फेज एंगल्स का भी पता चलेगा. I1 प्लस का फेज एंगल कितना है, IB1 प्लस का फेज एंगल और IC1 प्लस का फेज एंगल. स्टेप 3 में आपको अब क्या करना है? इन स्टेप 3 find phase angles of DVR compensation voltages or DVR injection voltages as what will be voltage of VAF1. इसका एंगल होगा IA1 जो आपने यहाँ स्टेप 2 में निकाला प्लस shifted by 90 degrees. Similarly, VBF1 will be equal to IB1 plus 90 degrees, and phase angle of VCF1 will be equal to phase angle of IC1 plus 90 degrees. This is step 3. Step 4 में वही करना है आपको. You have two equations with you, equation A or equation B. Now if you have feeder information about feeder impedance, you can use type 1 control, hence equation A. And if you don't have information about feeder impedance, you can use type 2 control, that is equation B. So step 4, find VFA1 star, VFB1 star, VFC1 star from equation A using type 1 control, or from equation B using type 2 control. So this is what your control algorithm will do. Depending upon which equation you use, your control algorithm will then calculate VFA1, RMS value of the fundamental component of compensation voltages, VAF1. So let us take this type 2 control. Type 2 control means these are the equations. VFA1 square, of course, star, minus 2A1 VL into VFA1 star plus VL square minus VTA plus square, TA1 plus square equal to 0. What is VTA1 plus? It is the fundamental component of terminal voltage. Similarly, VFB1 square minus 2AB1 VL VFB1 star plus VL square minus VTB1 plus square equal to 0, and VFC1 square minus 2AC1 VFC1 star plus VL square minus VTC1 plus square equal to 0. These are equation B for 3 phases. यहाँ से आपको VFA1 star मिलेगा. This equation will give you VFB1 star for phase B, and this equation will give you VFC1 star for phase C. So the 3-phase compensation voltages, but fundamental components you got to know. So you can find in your control algorithm, once you know the phase angle of these injection voltages, so AA1, AB1, AC1, you know load voltage, you can sense load voltage, you already know in step 1 you have already found the fundamental components of these terminal voltages. Substitute in this, so your control algorithm will solve these 3 equations, and it will give you the fundamental component of 3-phase injection voltages or 3-phase compensation voltages, VFA1 star, VFB1 star, and VFC1 star. But the problem is that these will take care of only fundamental component. I mean, they will make load voltage, they will regulate the load voltage, but they will consider only the fundamental component. But since your system is non-sinusoidal, in addition to fundamental component, it has harmonics also. It will not do, these compensation voltages will not do the harmonic compensation. And since your 3-phase voltages are unbalanced also, so this will not take care of unbalance also. So how to do that? So before I come to that, let me tell you that your control algorithm will now find instantaneous fundamental voltages, like VFA1 will be equal to root 2 VFA1 star will be equal to root 2 VFA1 star sine of omega t plus angle of VFA1. Okay, VFA1 star आपको यहाँ से मिला. So what is this is the RMS value, and instantaneous value is this fundamental component का. VFB1 star will be root 2 VFB1 star into sine of omega t minus 120 degrees plus phase angle of VFB1, which you have calculated in probably step number 2, these phase angles. And VFC1 star, instantaneous value of compensation voltage of phase C, VFC1 star, is equal to root 2 VFC1 star. This is the RMS value of compensation voltage of phase C, sine of omega t plus 120 degrees plus phase angle VFC1. Okay, ये तो पता चल गया, but it will not take care of harmonics and unbalance. Okay, so this was probably step 4. Then you need one more step, step 5. In step 5, what you will do, you will write now since your terminal voltage is, say, for phase A, it is VTA1 plus VTA rest. We have already resolved it into fundamental component, positive sequence fundamental component, and rest components. Okay, we have done it in step number 1 itself. And these equations will take care of only fundamental component of terminal voltages. And what about this rest? This rest comprises of negative sequence component and harmonics. So in order that the negative sequence component of voltage is not injected into the load, and the harmonics are also not applied across the load, this negative sequence component of voltage, which is coming from the source, and the harmonics, which are also coming from the source, they should be cancelled. So therefore VFA rest, that means your compensator should not inject only the fundamental component, it should inject this rest also. VFA star rest, it should be equal to minus VTA rest. Whatever is the harmonics present in the voltage and unbalance, that should be cancelled by injection voltage. So injection voltage or compensation voltage, in addition to injecting the fundamental component of compensation voltage, it should inject this unbalanced component, and it should inject the harmonics, which are equal to minus VTA rest, so that when these harmonics and these unbalanced voltages are injected, they cancel the already present unbalance and harmonics present in the voltage, and so that your load voltage becomes absolutely sinusoidal and regulated. Sinusoidal, balanced, and regulated. Similarly, your compensator phase B will inject the voltage VFB star rest, which is equal to minus VTB rest. And for phase C, VFC star rest is equal to minus VTC rest. Right? So therefore, what is the total injection voltage? Thus, total reference injection or reference compensation voltages are आपका compensator DVR जो है, it will first inject in phase A the voltage VFA, which is equal to fundamental component VFA1 star, जो अभी थोड़ी देर पहले हमने निकाला है in step number 4, plus VFA star rest, जो हमने ऊपर से निकाला, which is equal to minus VTA rest. Similarly, VFB star, the reference injection or reference compensation voltage for phase B, is equal to fundamental component of phase B injection voltage plus VFB rest. And VFC star is equal to VCF1 star. This is VA1F, VB1F, and VC1F. VC1F star plus VFC rest. So therefore, these fundamental components, they will regulate the load voltage. When there is a drop across the feeder impedance, they will ensure that load voltage is same as source voltage. And what will these rest components do? They will cancel the unbalance and they will cancel the harmonics which are present in the source voltages. So therefore, आपका three-phase load जो है, three-phase load will get regulated. That is constant voltages VLA, VLB, and VLC, which are constant and which are free of harmonics and which are balanced voltages. This is how it will do. Okay, so this is how you have to design your control algorithm. How your control algorithm will implement these steps. How will it will find the fundamental component of positive sequence component of these these voltages, the terminal voltages, and rest, VTA rest, VTB rest, VTC rest. How it will find fundamental component of positive sequence component of currents, extract them from the actual sensed currents using Fourier transform. How it will find angles, phase angles of these, and using equation A or equation B, how it will find fundamental component of these voltages, VFA1, VFB1, VFC1, and how it will find VFA rest, VFB rest, and VFC rest, and how it will find, using step number 5, the total reference compensation voltages VFA star, VFB star, and VFC star by adding like this. And when your voltage source or injection voltages are these VFA star, VFB star, VFC star, they will take care of voltage unbalance, voltage harmonics, and also they will take care of voltage drops, voltage changes, and they will make load voltages absolutely regulated, balanced, and harmonic free. Okay, this is how a critical load or voltage sensitive load will be protected from unbalance, from harmonics, and from voltage variations, right? So this control algorithm can be implemented using any digital signal processor, because you can implement these 4-5 steps using mathematical equations the way I have shown you, and it can be implemented using a computer program, using a digital signal processor or a microprocessor, where the voltages are sensed by the voltage sensor, currents are sensed by current sensors. The information about sensed voltages, sensed currents is given to the processor, and the processor implements these 5 steps mathematically, and it computes the 3 reference injection voltages, VFA star, VFB star, and VFC star. These are the voltages which your DVR should inject in series with load buses. This should be your VFA star, and this should be VFB star, and this should be VFC star for series voltage compensation. Now the question is how to synthesize these voltage sources. These voltage sources can be practically realized or synthesized using a 3-phase voltage source inverter, which is called DVR. Okay, I will now write here a realization, practical realization, or simply I can write realization of DVR compensation voltage. Realization of DVR compensation voltage using VSI, voltage source inverter, which will act as a DVR, dynamic voltage restorer. So simple schematic diagram is like this. This is your source voltage Vs. This is the feeder resistance, feeder reactance Rs, Jxs. This is the load current or source current Is. This is terminal voltage at the point of common coupling. This is PCC. Then you will connect DVR here. This is the DVR. Let me first complete. This is filter capacitor CF, and this is the DVR injected voltage VF. Okay. And this is the secondary winding of injection transformer, and this is the primary winding of injection transformer. Now I will have a voltage source inverter here. Let me draw the voltage source inverter circuit diagram first, then I will explain. I am taking one single phase voltage source inverter. This is the DC bus voltage, this is DC bus capacitor CDC, and this is the DC bus voltage VDC. Okay, this is switch S1, say switch S2, switch S3, and switch S4. These switches may be IGBTs. These are anti-parallel or feedback diodes D1, D2, D3, and D4. Right? Now, this is RT, this is LT. Let me write first, then I will explain. And this is inverter current I or injection current IF, or let me call this I inverter output current. Okay, so this is one inverter for one phase. Now you can use the same DC bus for other phases, two other phases. I mean, you may have similar single phase inverter for phase B and similar single phase inverter for phase C. I am showing for one phase. Okay, so this is your load voltage VL here, and this is your load. This is the load, and load current is IL. Okay, so this is very interesting. This is your distribution system. This is source voltage, source bus voltage. This is feeder resistance. This is the voltage at point of common coupling or terminal voltage VT. This is load voltage, and this is load current, which is same as source current. This is the DVR injected voltage in one phase, VF. Similarly, I am not showing all the three phases. I am showing for one phase. For other phases also you will have similar arrangement, but those injected voltages will be 120 plus minus 120 degrees displaced with respect to each other. I am showing operation for one phase, right? Now my aim is that this injected voltage VF, or let me call this VFA, it should be same as VFA star, which is calculated or which is found by your control algorithm using those 4 to 5 steps which I have already explained. In order to synthesize this voltage, VFA star, VFB star, VFC star, these voltages are synthesized by this voltage source inverter. Yeah, आपका voltage source inverter है, which acts nothing but which acts as a dynamic voltage restorer, DVR. Now the job of the control algorithm is to find these VFA star, VFB star, VFC star, and then I will implement a modulation algorithm. What will modulation algorithm do? It will control the switching of these switches S1, S2, S3, S4 in such a way that this is the inverter, it converts DC into AC in such a way that the AC voltage across the primary and AC voltage across the secondary VFA, which is injected in series with the load. Okay, this VFA is same as VFA star, which is calculated or which is computed by your control algorithm for phase A. Similarly, for phase B, VFB should be same as VFB star, and VFC for phase C should be same as VFC star. Because we have calculated this using the control algorithm, those 5 steps, we have calculated VFA star, VFB star, VFC star for protecting our load from voltage variations, voltage drops, and also for protecting our load from harmonics, and also protecting our load from voltage unbalance, so that the voltage, 3-phase voltage which is applied across the load is perfectly balanced, and this 3-phase voltage is sinusoidal and it is regulated, so that load voltage is same as source voltage, regulated voltage. Even if there are dips, sags or swells or flickers in the source voltage, or there is voltage drop across the feeder, but load voltage is maintained same as source voltage, it is regulated. So therefore, the switching of this inverter, which is a DVR, it has to be done in such a way that these voltages VFA star, VFB star and VFC star are synthesized. Okay, इसका equivalent circuit, its equivalent circuit is something like this. मैं यहाँ से दिखाऊंगा. This is the terminal voltage VT. उसके बाद आपका DVR है. So this is primary winding of your injection transformer, and this is the secondary winding of your injection transformer. The question is, why do we use transformer? हम directly ये injection voltage यहाँ क्यों नहीं across, directly यहाँ series में क्यों नहीं connect करते? I could have connected this terminal here, तो ये मुझे transformer की ज़रूरत नहीं थी. The answer to this question is that this feeder may be at high voltage, and your DVR may be generating or producing the injection voltage at low voltage. So to take this low voltage to high voltage level, you need a step-up transformer. So this will take care of that voltage difference. Secondly, this acts as an isolation transformer, and it provides electrical, this interfacing or injection transformer provides electrical isolation between various inverters. This is inverter for one phase. Similarly, you have inverter for phase B, inverter for phase C. So those 3 inverters are electrically isolated with respect to each other with the help of this injection transformer. It provides electrical isolation. Okay. So therefore the DVR or inverter यहाँ जो आउटपुट वोल्टेज होगी, इन्वर्टर की आउटपुट वोल्टेज ऐसे होगी, प्लस VDC माइनस VDC. I mean when switch S2 and S4 are on, when switch S2 and S4 are on, जब switch S2 on हो गया तो 1 minute, when switch S1 and S3 are on, this pair of switches is on. When S1 is on, अब देखिए ये terminal through S1 is connected to positive bus, and when S3 is on, ये terminal, it is connected to negative bus. So how much voltage is there across this and this? Plus VDC. ये positive होगा, this is connected to positive DC bus. This terminal is connected to negative DC bus. So therefore voltage here is plus VDC. ये plus VDC के बराबर है. और जब ये pair of switches on होते हैं, S2 and S4, when S4 is on, ये terminal अब negative bus के साथ connect होगा और ये positive terminal के साथ. तो how much voltage is there across the inverter? Inverter के output पे minus VDC होगी. So inverter के primary पे इस तरह की voltage available होगी. Let me show that here. Plus VDC minus VDC, plus VDC minus VDC, plus VDC minus VDC, like this. Okay, so this is inverter output voltage, V inverter. Now ये inverter output voltage, इसमें high frequency ripples है, high frequency components है, because suppose you are switching this inverter at 20 kilohertz, तो इसमें 20 kilohertz और उसके 40 kilohertz and 60 kilohertz high frequency harmonics होंगे, and we want to we want to suppress those harmonics. वो harmonics suppress करने के लिए हम filter use करते हैं. ये inductance जो मैंने यहाँ दिखाई है, it may be transformer leakage inductance and some external inductance, and ये capacitance, ये भी filter capacitance है. So this inductance and this filter capacitance, they act as a filter together. So this is XT reactance and this is CF, sorry, this is RT, transformer की resistance होगी है, and across this inverter I have CF. So ये voltage होगी VF के बराबर, ये आपकी load voltage है, and this is load here. What is this RT? RT is the resistance. It is not a physical resistance that I have connected. It represents the power losses, switching power losses in the inverter, and it represents the copper losses in the transformer. It is just a model. Model में हम ये RT दिखाते हैं. It represents the transformer copper losses and inverter switching power losses. And this LT represents the transformer leakage reactance and some maybe external inductance, and this is the filter capacitance CF. So therefore inverter output voltage is, this it's PWM voltage, pulse width modulated voltage. To remove the high frequency harmonics from it, we have these filter X and C. So what these are called ripple filters. This X and C, this is called ripple filter. इसको हम ripple filter कहते हैं. What will these ripple filters do? ये inverter की output voltage में से सारे high frequency harmonics निकालेंगे in such a way that ये जो आपकी inverter output voltage VF है, which is compensation voltage, yes, let us call this VFA. It will be same as VFA star. Okay. Similarly, दूसरे phases में भी ऐसे ही होगा. Now the question is, so this is how you get VFA equal to or same as VFA star. Similarly, VFB will be same as VFB star. VFC will be same as VFC star. Now the question is, how do we do the switching of these IGBT switches in such a way that VFA is same as VFA star for phase A, for phase B, VFB is same as VFB star, and for phase C, VFC is same as VFC star. उसके लिए आपको modulation algorithm use करना है, and I will explain to you hysteresis current controller. So what is the modulation algorithm that we are using? Control algorithm, what is the, देखिए आपके इसमें दो चीजें होती है. एक तो है कंट्रोल एल्गोरिथम या कंट्रोल थ्योरी. कंट्रोल एल्गोरिथम का काम क्या है? टू फाइंड दीज रेफरेंस कंपनसेशन वोल्टेजेस VFA स्टार, VFB स्टार एंड VFC स्टार, जो हमने पिछले 4-5 स्टेप्स में निकाला. Using we have extracted the voltages, terminal voltages, we have extracted the fundamental component of positive sequence currents, we have computed the phase angle of these compensation voltages, and from equations A or B, we have calculated these VFA star, VFB star, VFC star. This is the job of control algorithm. And after sensing the terminal voltages, load voltages and load currents, we feed those to microprocessor, और microprocessor में already आपने वो पांचों step implement किए हैं through mathematical equations. Those computations will be done in the digital signal processor, and it will generate VFA star, VFB star, VFC star. Once these VFA star, VFB star, VFC star are generated, now we want that our actual DVR or inverter voltages should be synthesized, should be same as, that means VFA should be same as VFA star, VFB, which is the voltage, it should synthesize VFB star, and VFC, which is the injection voltage of VFC, should be same as VFC star. वो करने के लिए आपको इन्वर्टर की स्विचिंग कंट्रोल करनी है, and to generate the switching pattern of the inverter, that's DVR, we use modulation algorithm. Modulation algorithm का काम है ये voltages synthesize करना, VFA, VFB, VFC, which are same as VFA star, VFB star and VFC star. How does modulation algorithm synthesize these voltages? By proper switching of the inverter switches. तो modulation algorithm का काम है to generate control pulses for switches and control switching of DVR inverter in such a way that reference compensation voltages are synthesized. Reference compensation voltages are synthesized. आपकी जो इन्वर्टर की आउटपुट वोल्टेजेस हैं वो एग्जैक्टली होंगी ये रेफरेंस कंपनसेशन वोल्टेजेस के बराबर. दिस इज द जॉब ऑफ मॉड्यूलेशन एल्गोरिथम. और जो मॉड्यूलेशन एल्गोरिथम मैं आपको यहाँ दिखाऊंगा, देयर आर मेनी मॉड्यूलेशन एल्गोरिथम्स. अगर आप लिटरेचर देखेंगे, different researchers have used different modulation algorithm. I will use hysteresis current controller, जो मैंने DStatCom में भी आपके साथ explain किया है. I have explained that for DStatCom. Hysteresis controller. Now suppose this is your VFA star. I don't know the shape of VFA star. It may be any shape. Suppose this is VFA star. What we do is, this is your VFA star, that's reference compensation voltage. I want my actual voltage should be same as reference compensation voltage. So I create a band, upper band around this, and I create a lower band around this. मैं एक half cycle आपको दिखाऊंगा. I will show you one half cycle. Same is that true for negative half cycle. So this, ये band जो है, this is plus H, और ये lower band जो है ये minus H है. And I will do the switching of inverter in such a way कि inverter की voltage जो है ये पहले rise होगी, और जो ही ये upper band को touch करेगी, inverter की switching control होगी, ये voltage decrease होगी. And जो ही ये lower band को touch करती है, inverter की switching फिर से change होगी. And therefore your actual voltage, ये जो है ये rippled voltage, ये actual voltage है. It will very closely follow VFA star within the hysteresis band. Now you may again raise a question, sir, this VFA is following VFA star, but इसमें ripple content ज़्यादा है. आपकी VFA कुछ ऐसे है, लेकिन VFA star कुछ ऐसे है, इसमें ripple ज़्यादा है. Actually ये ripple इसलिए है, मैंने यहाँ band ज़्यादा दिखाया, लेकिन actual में इतना बड़ा band नहीं होता. अगर ये आपकी ripple ये VFA star है, आपकी ये actual voltage VFA within a very narrow band, it will be same as this, to very closely follow this. So this will be VFA. So VFA will be very nearly following VFA star. So you have to make band very, very low. Okay. So यह आपका inverter है. DVR, of course, DVR inverter. मैं फिर से पार्ट ऑफ दैट सर्किट आई एम ड्राइंग फॉर यू। और आपका इंजेक्शन ट्रांसफार्मर ये है। This is connected here and this is connected here. This is V inverter and ये कैपेसिटर है। This is VF आउटपुट पे वोल्टेज। Okay, so this is S1 D1 S2 D2 S3 D3 S4 D4. This is your inverter, voltage source inverter, which is nothing but a DVR, dynamic voltage restorer. इसकी ये DC बस है। मैं एक फेज का दिखा रहा हूँ। सेम इज ट्रू फॉर अदर फेजेस। दिस इज DC bus capacitor and this is DC bus voltage. Okay, the logic is like this. What is the logic? If VF is greater than or equal to, let us first of all define these two voltages. VF up is equal to VF star plus H. यह आपकी VF स्टार है और ये अपर हिस्टैरिसीस बैंड है। VF स्टार देखिए, मैं यहाँ फिर से क्लियरली दिखाना चाहता हूँ आपको। दिस इज योर VF स्टार और ये इसका ऊपर वाला बैंड है। दिस इज H. सो व्हाट इज दिस? दिस इज VF स्टार प्लस H और लोअर बैंड ये है। दिस इज माइनस H और ये क्या है? दिस इज देन VF star minus H. So VF up is VF star plus H and VF down is equal to VF star minus H. Yeah. So this is VF star plus H everywhere and this is everywhere VF star minus H. And logic is if VF is greater than or equal to VF up, that means let us suppose ये पेयर ऑफ स्विचेस हम ऑन करते हैं, S1 और S3 ऑन है। When S1 and S3 is on, what is your output voltage? It is plus VDC. Okay? और फिल्टर इसमें से रिपल्स निकाल के ये वोल्टेज को सेम बनाएगा VF स्टार और what will happen? Your voltage will start rising. Output voltage will start rising. As soon as it touches the upper band, that means as soon as VF is greater than or equal to VF up, ये स्विचिंग पैटर्न चेंज होना चाहिए। तो यहाँ S1 और S3 ऑफ होने चाहिए। ओके, सो S1 S3 शुड बी टर्न ऑफ और कॉम्प्लीमेंट्री स्विचेस जो अपोजिट स्विचेस हैं S2 एंड S2 S4 शुड बी टर्न ऑन। अब ये दो ऑफ हुए और ये दो ऑन हुए। जब ये दो ऑन होते हैं तो व्हाट वोल्टेज इज इम्प्रेस्ड अक्रॉस द इंजेक्शन ट्रांसफार्मर? माइनस VDC। माइनस VDC का मतलब हुआ ये वोल्टेज अब ड्रॉप हो जाएगी, वोल्टेज अब फॉल होना शुरू हो जाएगी। और जब वोल्टेज फॉल होती है ये धीरे धीरे फॉल होती है और ये नीचे वाले बैंड के साथ लग जाती है, VF डाउन के साथ। ओके, एल्स इफ VF इज लेस देन और इक्वल टू VF डाउन, जो ही ये लेस देन और इक्वल टू VF डाउन के साथ टच करती है इस लोअर बैंड के साथ, तो कंट्रोल लॉजिक अब चेंज होगा। दैट मीन्स S2 S4 पहले ऑन थे, अब ये ऑफ हो जाएंगे। S2 S4 शुड टर्न ऑफ और ऑपोजिट स्विचेस, कॉम्प्लीमेंट्री स्विचेस S1 S2 शुड टर्न ऑन। जब S1 S2 फिर से ऑन हो जाएगी, ये पॉजिटिव फिर से हो जाएगी, पॉजिटिव वोल्टेज का मतलब हुआ ये फिर से राइज हो जाएगी। उसके बाद ये कंटिन्यू। और अगर आपकी वोल्टेज बीच में है, ना तो ये लोअर हिस्टैरिसीस बैंड पे है ना अपर हिस्टैरिसीस बैंड पे है, बीच में है, तो आपको स्विचिंग पैटर्न चेंज नहीं करना है। वो लॉजिक भी आपको लिखना है प्रोग्राम में, कंप्यूटर प्रोग्राम में। एल्स इफ VF डाउन लेस देन और इक्वल टू VF, इट्स नॉट लेस देन और इक्वल टू, लेस देन VF, लेस देन VF अप। अगर आपका VF ये वोल्टेज ग्रेटर देन VF डाउन है लेकिन लेस देन VF अप है, दैट मीन्स बीच में है, ना तो अपर हिस्टैरिसीस बैंड को टच कर रही है ना लोअर हिस्टैरिसीस बैंड को टच, तब आपको स्विचिंग पैटर्न चेंज नहीं करना है। रिटेन द करंट स्विचिंग स्टेटस, तो उसको रिटेन कर लीजिए जो भी स्विचिंग स्टेटस है, वेदर ये पेयर ऑफ स्विच ऑन है या ये पेयर ऑफ स्विच ऑन है। रिटेन द करंट स्विचिंग status end. तो इसके साथ प्रोग्राम आपका एंड हो जाएगा. That's it. तो you have to write a control और ये आपका modulation algorithm है. इसको hysteresis controller कहते हैं because your voltage is between this hysteresis band. It neither goes beyond this hysteresis band ऊपर की तरफ ना तो नीचे की तरफ नीचे जाती है. Your hysteresis controller keeps this filter voltage or compensation voltage within this hysteresis band and it very closely follows VF star. Okay, so VF is same as VF star within a very narrow hysteresis band जो मैंने यहाँ दिखाया. This is the logic. This is how it works. Okay. अब इसमें एक और चीज आपको ऐड करनी है. One more thing you have to add in this control algorithm. जो मैंने उसमें भी बताया आपको DStatCom में भी. That is about the losses. Losses कहाँ से आएंगी? ये आपका voltage source inverter है. This is your voltage source inverter. Now, when these switches are turning on and off at a very high frequency, maybe 10 kilohertz, 20 kilohertz, or more than 20 kilohertz, and because of their switching at very high frequency, there will be switching power losses. And there will be copper losses in the transformer also. And these switching power losses and copper losses are modeled by RT, resistance जो मैंने यहाँ दिखाई है. So इसमें loss होगी I square RT loss. Now this I square RT loss will include transformer copper loss as well as switching power losses of this inverter. ये losses अगर DC bus यहाँ supply कर रही है, so DC bus will keep on supplying these losses. नतीजा उसका ये होगा, the result will be that this DC bus capacitor के across जो voltage है वो fall होगी और ultimately DC bus capacitor fully discharge होगा और ये DVR जो है which is basically an inverter, it will stop functioning. See, inverter functions only when there is DC bus voltage available across its DC bus because inverter basically converts this DC into AC. और जब DC voltage ही collapse हो गई, so it will not function, it will not inject any voltage. So therefore your job is, your control algorithm has also to ensure that when DVR is working, these switching power losses and transformer copper losses, they should not be supplied by the capacitor, DC bus capacitor. They should come from the source. ये आपका source है VS, यहाँ से आनी चाहिए. So उसके लिए आप क्या करेंगे? You will put a voltage sensor here. It will sense the DC bus voltage VDC. उसको आप compare करेंगे reference DC bus voltage से VDC star. Let us suppose reference DC bus voltage 600 volts है. आप 600 volts DC bus voltage ये DC 600 volts कहाँ से आ गई? ये डिजाइन आपको प्रॉपरली डिजाइन करना है. यू हैव टू डिजाइन द डीवीआर डिपेंडिंग अपॉन कंपनसेशन. आपको कितनी करनी है? आपको डीसी बस वोल्टेज सिलेक्ट करनी पड़ती है. उसके लिए एक अलग डिजाइन प्रोसीजर है. एंड लेट अस सपोज आफ्टर डिजाइनिंग द डीवीआर द डीसी बस वोल्टेज दैट यू हैव कैलकुलेटेड इज 600 वोल्ट्स. नाउ दिस डीसी बस वोल्टेज VDC शुड बी इक्वल टू रेफरेंस वोल्टेज 600 वोल्ट्स. ये ड्रॉप नहीं होनी चाहिए. But if power losses are not supplied by the source, then this DC bus capacitor will supply all the switching power losses and transformer copper losses. और ये DC bus voltage 600 volt पे maintain नहीं रहेगी, ये fall हो जाएगी और ultimately DC bus voltage will collapse and inverter will stop working and there will be no injection voltage here. To avoid that situation, you have to use this comparator. This comparator will compare the actual DC bus voltage with reference DC bus voltage. And if your DC bus voltage is less than reference DC bus voltage, it will give error. It will produce error EVDC, जो ये PI controller में देगा. PI voltage controller. PI voltage controller. और ये PI voltage controller एक quantity से एक control signal इसके output पे निकलेगी VC. वो VC अब what is that VC equal to? This VC is equal to Kp into EVDC plus Ki integral 0 to Td EVDC dt. I have already explained it in DStatCom. Same equation. In each cycle of source voltage, this DC bus voltage will be sensed, or a sample of DC bus voltage will be taken. It will be compared with reference, and if there is any error, that is given to PI voltage controller, और PI voltage controller ऐसे PI processing करता है. KP and KI are the gains of the PI controller. Okay, this is how PI controller works. और PI controller का काम है कि ये control signal इस तरह से produce करे that this error becomes zero, EVDC becomes zero. When will be EVDC equal to zero? When VDC is exactly equal to VDC star. और जब ये DC bus voltage reference पे मेंटेन रहती है. दिस इज द जॉब ऑफ PI वोल्टेज कंट्रोलर टू मेंटेन दिस वोल्टेज कांस्टेंट. लेकिन ये वोल्टेज तभी कांस्टेंट रहेगी जब ये फॉर एग्जांपल दिस वोल्टेज फॉल्स, यहाँ से पावर आना चाहिए और ये कैपेसिटर फिर से वापस चार्ज होना चाहिए एंड इट शुड रिटेन द वोल्टेज एट 600 वोल्ट्स. ओके, वो पॉसिबल तब है जब आप देखिए आपका जब आप फिल्टर वोल्टेज निकालते हैं VF1, that is equal to VF1 at an angle of say I plus I1 plus 90 degrees. ये एंगल आपने निकाला. That means जो DVR यहाँ वोल्टेज इंजेक्ट करता है that should be at 90 degrees to current. That means अगर ये सोर्स करंट है, से सोर्स करंट है, इंजेक्टेड वोल्टेज इज एट 90 degrees, so that उसका मतलब DVR खाली रिएक्टिव पावर इंजेक्ट करता है, एक्टिव पावर इंजेक्ट नहीं करता. लेकिन अगर आप ये एंगल थोड़ा चेंज करेंगे, फॉर एग्जांपल ये अगर सोर्स करंट है, एंगल ऑफ 90 डिग्री से थोड़ा कम रखेंगे, से 85 डिग्रीज, 5 डिग्रीज जो इसमें डिफरेंस आएगा उससे क्या होगा, इट विल इंजेक्ट, अभी भी ये रिएक्टिव पावर इंजेक्ट करेगा बट इट विल ड्रॉ एक्टिव पावर. व्हाई इट विल ड्रॉ, क्योंकि इसमें 5 डिग्री का डिफरेंस है. इट इज नॉट 90 डिग्री, इट इज 85 डिग्रीज. जो 5 डिग्री का डिफरेंस है, सो वो जो सोर्स वोल्टेज है, सोर्स वोल्टेज विल लीड द इंजेक्शन वोल्टेज बाय दिस डिफरेंस 5 डिग्रीज. और मैंने कल भी आपको बताया, जब एक वोल्टेज दूसरी वोल्टेज को लीड करती है, जो वोल्टेज लीड करती है वो पावर डिलीवर करती है. सिंस सोर्स वोल्टेज लीड्स DVR compensation voltage say by for example 5 degrees or it may be 10 degrees, ये डिपेंड करता है. तो ये सोर्स से पावर डिलीवर होगा. सोर्स इस इन्वर्टर को पावर डिलीवर करेगा, ये AC पावर होगा, और ये इन्वर्टर एज अ रेक्टिफायर एक्ट करेगा. वो इस AC पावर को DC पावर में कन्वर्ट करके कैपेसिटर को चार्जिंग करंट देगा IDC, और कैपेसिटर चार्ज होगा और इसकी वोल्टेज, और जब इसकी वोल्टेज बराबर VDC 600 वोल्ट्स VDC रेफरेंस के बराबर आ जाती है, देन नो पावर विल कम. और जो ही ये कैपेसिटर वोल्टेज फिर से फॉल होना शुरू हो जाती है बिकॉज इट इज सप्लाइंग दीज लॉसेस, तो फिर से पावर यहाँ से आता है और कैपेसिटर वोल्टेज वापस अपनी रेफरेंस वैल्यू पे आ जाती है. सो देयरफॉर आपको ये एंगल जो है कंपनसेशन वोल्टेज का है, ये चेंज करना है. ये आपने लिखा था VF I1 प्लस 90 डिग्रीज, इसको माइनस VC कर लीजिए. जो यहाँ PI वोल्टेज कंट्रोलर ये कंट्रोल सिग्नल देगा, वो इसमें से सब्ट्रैक्ट कर लीजिए. वो करंट और वोल्टेज के दरमियान 90 डिग्री नहीं रखेगा आप, 90 डिग्रीज माइनस VC से VC 5 डिग्रीज हो सकती. सो 90 माइनस 5 मीन्स ये 85 डिग्रीज पे इस फेजर को रखेगा, VF फेजर को. और उससे क्या होगा, व्हाट विल हैपन, VS विल लीड VF बाय दिस 5 डिग्रीज, और इट डिपेंड्स अपॉन कितने डिग्री, मे बी इवन मोर देन 5 डिग्रीज, एंड पावर विल फ्लो इन दिस डायरेक्शन एंड इट विल keep on charging the capacitor to maintain the capacitor voltage at reference value, so that VDC is equal to VDC star maintained at 600 volts. Okay, so therefore this will be VF1 A1 plus JB1 आप लिखते थे, वो उसमें A1 plus JB1 आप ऐसे लिखेंगे, A1 plus JB1 आप ऐसे लिखेंगे. और उससे जो आपकी ये इक्वेशन थी VF1 स्टार स्क्वायर माइनस 2A1 आप ऐसे सिंबल दे दीजिए, V1 F1 स्टार प्लस VL स्टार माइनस VT1 स्टार इक्वल टू 0. ये जो आपकी इक्वेशन B थी टाइप 2 कंट्रोल, उसमें ये A1 मैं लेता था ऐसे, नाउ आई विल टेक इट A1. और ये A1 का मतलब क्या हुआ, A1 का मतलब हुआ अब यहाँ माइनस VC, जब माइनस VC यहाँ होगा तो यहाँ फेज एंगल थोड़ा सा चेंज होगा. जो आपका रियल और रिएक्टिव पार्ट आता था वो स्लाइटली डिफरेंट आएगा, सो दैट पावर फ्लोज फ्रॉम सोर्स टू इन्वर्टर एंड दैट चार्जेस द कैपेसिटर. ओके, दिस इज हाउ योर hysteresis controller works. modulation algorithm works. So you have to first implement control algorithm through digital signal processor after sensing voltages and currents, load voltages, terminal voltages, and load currents. When those sensed voltages are given to processor, then you have different mathematical equations there. Those mathematical equations are implemented. What will those mathematical equations do? They will find the phase angle of this compensation voltage, which is not I1 plus 90 degree, which is I plus 90 degrees minus VC. और ये VC कहाँ से आएगा? PI voltage controller से आएगा, यहाँ feedback loop से आएगा. And it will find A1 plus JB1. A1 आपका यहाँ से निकलेगा. It will substitute in this equation. VL तो sensed voltage है. VT1 भी आप फोरियर ट्रांसफॉर्म से पहले टर्मिनल वोल्टेज सेंस करते हैं, उसमें से फंडामेंटल कंपोनेंट निकालते हैं और यहाँ से आपका VF1 निकलेगा. VF1 निकलने के बाद आपको एक्चुअली VF चाहिए. एंड व्हाट इज दैट VF स्टार? दैट इज VF1 स्टार प्लस VF रेस्ट स्टार. वो रेस्ट वगैरह, व्हाट इज दैट VF रेस्ट इक्वल टू? दैट इज इक्वल टू माइनस VT रेस्ट. जब आपने टर्मिनल वोल्टेजेस सेंस की, वहां से आप फंडामेंटल कंपोनेंट जब निकालोगे, जो बाकी बचता है वो VT रेस्ट है. दैट कंट्रोल एल्गोरिथम विल मैथमेटिकली डू. इट विल split, it will divide the VT into fundamental component and rest, and then it will make VF rest equal to minus VT rest in this mathematical equation. And after implementing these equations, it will generate this control algorithm will generate three compensation voltages: VF star, VFA star, VFB star, VFC star. Then DVR will synthesize these voltages by switching off the switches in such a way that using the hysteresis controller, the injected voltage or compensation voltage VFA is nearly same as VFA star within the small hysteresis band. Same is true with VFB, same is true with VFC. And that is the modulation algorithm. So which modulation algorithm we are using here? I have discussed with you hysteresis controller. In hysteresis controller, the logic I have given you, how VFA, VFB, VFC is synthesized by this voltage source inverter, by this proper switching. So this, after implementing this modulation algorithm, the control pulses are generated by the modulation algorithm for all the 4 switches, and then those control signals are connected at the gates of the 4 IGBTs, and the switching of these switches is done in such a way that VFA follows VFA star, VFB follows VFB star, VFC follows VFC star within narrow hysteresis band. And the injection voltages take care of all types of voltage related power quality problems, that like voltage unbalance, voltage harmonics, and voltage sags, voltage swells, voltage flickers, etc. And it makes load, it protects your load against all these types of voltage related power quality problems. So I hope you have understood. You will go through this lecture and you will revise this lecture and try to understand what I was trying to make you understand. This is very, very important, because those of you who want to implement this dynamic voltage restorer for series compensation or voltage compensation, for protecting your sensitive load or critical load against these voltage related power quality problems, you can take this as a project or as a dissertation. Some of you can take this as a dissertation in your MTech second year and third semester and fourth semester, and you can do your dissertation in this area. Okay. I am pleased to inform you that recently one of my PhD research scholars, Dr. Shubhendra Pratap Singh, he was earlier Mr. Shubhendra Pratap Singh. Now he has been awarded PhD degree recently, just 2 weeks back in the department. He did his PhD research on dynamic voltage restorer, DVR. He did his PhD on this topic itself, and he published very good publications in reputed Scopus Index journals. And his PhD thesis was evaluated by one of the professors in Texas University. He was his international examiner. And one of the professors from one of the NITs, he was his national examiner. And both of them recommended award of PhD degree. His work was appreciated by both the examiners. And just 2 weeks back, we held a defense or Viva Voce exam. His Viva Voce exam was held in the department, and he successfully defended his thesis, and he has been awarded PhD degree. He did his PhD under my supervision on this topic, dynamic voltage restorer. And my other PhD research scholar, Ms. Humaira, is this time working on the same problem, dynamic voltage restorer, but in a different way. Her topic is different, her control algorithm is different, and she is also in the final stage of her thesis. Hopefully within 5 to 6 months, she will also submit her thesis for award of PhD degree. So I am sharing this with you to just inspire you to take this as your project or dissertation. Those of you who are interested in studying the DVR, doing the project and dissertation on this topic. So for that purpose, you have to understand the basics of the dynamic voltage restorer, how it works, what is the control algorithm, how is the modulation algorithm implemented, and how voltage or series compensation is done by a DVR. So today's lecture, I hope, will be very beneficial to you. Please go through this lecture, and in case of any queries, please get connected to me. All the best. Thank you.